In this video, we're going to take a look at special right triangles. Now, up until this point, we've talked about triangles. We've talked about triangle sides and angles and solving for some of them. What we're going to start doing is we're going to start considering more different types of triangles that I can solve for. And what we're doing here is we're specifically going to look at two special types of triangles, the 45-45-90 triangle and the 30-60-90 triangle. And then we're going to see if we can notice some patterns that help us to solve those triangles that show up a lot in geometry, some patterns that help us solve them quickly. In a sense, this is a shortcut. But shortcuts are as valuable as they are useful. If they chop off a significant amount of time on your travels, if you think about a distance, then that's great. If you use it all the time, that's even better. Like say a shortcut from here to Wyoming that you find a special highway or something, not super helpful unless you're making trips to Wyoming all the time. But if you find a shortcut from your ride from school back home, then that's super helpful because you're using it all the time. So this, while I say it's a shortcut, don't feel like it's like, oh, well, I don't really need to learn this, because we're going to use this a ton. We're going to use it all the time in trigonometry, so it's absolutely worth learning. And so we're going to jump in here. I don't think it's that complicated. A lot of it's just memorization, which it sounds like, oh, well, I just need to memorize it. But you actually need to put the time and effort into memorizing these triangles. It's going to make trigonometry easier, and it's going to make what we move into with some other right triangle stuff also easier. So let's take a look at this first problem here. You kind of want to explore this a little bit and see what happens here. So I want you to solve for all the variables here. We're going to do that. The first thing we should probably do is solve for the missing angles, right? I've got a 90-degree angle. I also have an isosceles triangle. Remember, this triangle has two equal sides. So the isosceles triangle tells me that x and y are equal. And I also know they add up to 90. Right, because of the triangle. So I know x is equal to y. I also know x and y. X and y add up to 90. So obviously these are going to have to be 45 and 45. Okay, so I've got, this is my 45, 45, 90 triangle. I know that this side over here is 3, right, because they're equal sides. Now let's go ahead and solve for z. Now the way we have to solve for z right now, it just is Pythagorean theorem, right? So I'm going to do 3 squared plus 3 squared is equal to z squared. And 3 squared plus 3 squared, that's going to be 18 is equal to z squared. And let's take the square root of that. And I can actually factor out 18 into what? 2 times 9, root 2 times root 9. And root 9 is equal to 3 root 2. Okay? And so notice here that my z value ends up being 3 root 2. Now think about this. What if I'd done, oh, hang on, what just happened there? All right, there we go, sorry. Say I'd done 5 and 5. Well, it'd be 5 squared plus 5 squared, and then it would have been 50, which is 2 times 25, and that would have been 5 root 2. No matter which numbers I plug in here, my z value, this hypotenuse, always ends up being that value times root 2. And so actually here we find a pattern. For my 45, 45, 90 triangles, every single time there's the x value, which we'll call just our regular leg, and then the hypotenuse is root 2 bigger than times bigger than our leg. And so if I'm going towards the hypotenuse, I'm going to multiply by root 2, but if I'm going to go away from the hypotenuse, I'm going to divide by root 2. So let's look at an example or two here. So this is really simple, right? I'm just going to go from my leg to my hypotenuse, and just 6 root 2, done. That's a lot faster than doing Pythagorean theorem, right? And it's also an exact value rather than a rounded value. Let's look at another one. Okay, let's look at a couple of these. Okay, so 7 here would be 7 root 2, and then this side is just going to be 7 because those are the same. All right, let's look at B here. All right, well, in this case, I want to go 8 back to a side. Now again, I'm getting smaller. I'm going from the hypotenuse to a leg. So I need to do 8 divided by, sorry, let me put this in place so you can actually see everything. 8 divided by root 2. Okay. And then I'm going to multiply top and bottom by root 2. Okay. Why am I doing that? Well, we need to rationalize the denominator. We can't have a radical in our denominator. So I get 8 root 2 all over 2, and then I can actually simplify that. The 2 and the 8 comes out to 4 root 2. So my final answer here would be 4 root 2 and 4 root 2. Okay. The 20 was going to work similarly, and so we're going to keep moving on here. So that's our 45, 45, 90 triangle. Let's take a look at a 30, 60, 90 triangle. So maybe the easiest way here to think about this is thinking of a 60, 60, 60 triangle, or an equiangular or equilateral, equal angles, equal sides type of triangle. So in this triangle, I know I've got fours all around, right? Now, in the triangle on the right, what I've done is I've drawn a line straight down the middle of my triangle, okay? So this 4 at the bottom, that becomes 2 and 2, so x is equal to 2 here. All right, and then all we need to do is solve for y. Okay, so let's plug this in. 2 squared plus y squared is equal to 4 squared. So you get 4 plus y squared is equal to 16. I'm going to subtract 4 on both sides. Y squared is equal to 12, right? Take the square root of both sides. Y is equal to root 12. And then let's break root 12 up. I actually can pull out a 4, right? A 4 and a 3, and I end up with y is equal to 2 root 3, okay? So, at that point, we should be able to notice a little bit of a pattern here. Okay, so this is my shortest leg. Remember, triangle inequality tells me opposite to 30 degrees is going to be my smallest leg. So my smallest leg is 2. My biggest leg, or my medium side, my biggest leg is 2 root 3, and then my hypotenuse is 4. So that gives us this example right here. Whatever the smallest side is, the hypotenuse is twice as big, and the longer leg is root 3 times as big. So I like to think of it this way. I like to think of kind of that shortest side as being my home base. I want to get to the shortest side. If I don't have it, say I want to get there and then move to wherever I'm going. So if I'm given the hypotenuse trying to find the longer leg, instead of trying to come up with like a multiply by 2, divide by root 3 sort of situation, I would always just go back to your smallest side and then go forward to wherever you're going. So notice with 2, with the shortest leg to the hypotenuse, we're going to multiply or divide by 2. If it's getting bigger, I'm going to multiply by 2. If it's getting smaller, I'm going to divide by 2. Same with root 3. If it's getting bigger, I'm going to multiply by root 3. If it's smaller, I'm going to divide by root 3. So let's solve a couple problems here. We'll solve this one real quickly. So I'm getting larger. This is going to end up being 6 root, I'm sorry, not 6 root 2. This is just going to be 12, right? Multiplied by 2. Okay, and then if I'm going this way, it's getting bigger. I've got 6 root 3, and that's as far as that simplifies. Let's look at another one. Okay, what if I put the 6 on my hypotenuse? What am I going to do? Well, again, the first thing I'm going to do is I'm going to solve from my shortest side. And instead of multiplying by 2, I'm going to divide by 2. So 6 divided by 2 gets me 3. So x is equal to 3. And then this becomes 3 root 3. I'm going to multiply by root 3. Let's look at another one here. Okay, what if 6 is on the longer leg? Okay, let's take a look. So again, I'm getting smaller, so instead of multiplying by root 3, I'm going to divide by root 3. Oh no, I've got a radical in my denominator. I need to rationalize. I'm going to multiply top and bottom by root 3. So I get 6 root 3 all over 3, and then this simplifies down to 2 root 3. So x is 2 root 3. Let's solve for r. Going to multiply by 2, so I get 4 root 3. It's not 4 root 6. When we multiply the integers with integers, radicals with radicals. All right, last one. Say I've got a 30, 60, 90 triangle here, and let's say that, let's pick a good one here. We'll just keep it pretty simple. Let's say this is 7 root 2. Okay. Well, going to my hypotenuse, okay, and again, keep track of, I know we've rotated the triangle here, but going to my hypotenuse, I'm going to double, right? So this is going to be 14 root 2. And then going to my longer leg, I'm going to multiply by root 3. So this becomes 7 root 2 times root 3, or 7 root 6. Okay, now the reason this is important is it's always about the smallest side, okay? It's always the side opposite the 30 degrees that helps us get to the other sides, all right? So let's look at one more here. Let's say I know that this is, let's say I know this is 15 root 12. No, let's do 15 root, we'll just do 15 root 3. That's fine. Okay. Actually, sorry. Okay, last one, 14 root 3. Here we go. Real deal this time. All right, so again, I'm always going to get to my shortest side here. So this becomes 7 root 3. Okay, divided by 2. And then I'm going to go to my longest side here, or my longest leg, 7 root 3 times root 3, which that actually becomes 7 times 3, or 21. So hopefully that, now notice, even though I've got 21 here, that doesn't mean it's bigger than 14 root 3. I know it seems like it's bigger, but if we plug 14 root 3 in our calculator, we find out that's actually significantly larger than 21. So don't be freaked out if you see like 21 on a side that's not the hypotenuse and a small, what seems like a smaller number on the hypotenuse. So this wraps up special right triangles. You can go ahead and do your practice now.